The universe is a vast, uncharted expanse, filled with mysteries that defy our understanding. Imagine looking up at the night sky and realizing that what you see is just a fraction of what exists. Hidden patterns weave through the cosmos, guiding everything from the smallest particles to the largest galaxies. Scientists and theorists have spent lifetimes trying to uncover these secrets, and yet the universe keeps its deepest truths just out of reach. What if there are underlying principles, invisible threads that hold everything together? What if the cosmos operates under rules we're only beginning to glimpse? In this video, we'll explore 30 fascinating theories that shed light on the hidden patterns of the universe, from the mind-bending holographic principle to the elusive nature of dark matter and dark energy. Each theory opens a door to a new way of thinking, challenging what we know and inspiring us to ask questions we've never dared to ask before. Stay with us, and you'll uncover insights that could change the way you see the universe forever. Now let's dive into one of the most mind-bending ideas in modern physics, the holographic principle. Picture this: what if everything you see around you, from the stars in the sky to the ground beneath your feet, is actually a projection? This theory suggests that the universe might be a hologram, where all the information we experience in 3 dimensions is actually encoded on a 2-dimensional surface. It's like watching a 3D movie, except the screen is flat, and the illusion is so convincing that it feels real. The idea first emerged from the study of black holes, where scientists discovered that all the information falling into a black hole isn't lost but is instead stored on its surface, known as the event horizon. This led to the groundbreaking thought that perhaps the entire universe operates in a similar way. If true, it would mean that the reality we perceive is just a shadow of a deeper, more fundamental layer of existence. The holographic principle challenges our understanding of space, time, and even the nature of reality itself, opening up questions about what's truly real and what's just an elaborate projection. It's a theory that doesn't just change how we see the universe, it changes how we see ourselves within it. Now, let's shift our gaze to an even more expansive idea, the multiverse hypothesis. Imagine that our universe, vast and intricate as it is, might only be one tiny piece of an infinitely larger puzzle. This theory proposes that there could be countless other universes out there, each with its own set of physical laws, constants, and even realities that might look nothing like our own. The concept isn't just science fiction, it's rooted in serious scientific thought. For instance, quantum mechanics suggests that every possible outcome of a quantum event could spawn a new universe, leading to an endless branching of realities. Then there's cosmic inflation, the idea that our universe underwent rapid expansion in its earliest moments. Some scientists argue that this process could have created bubbles of space-time, each developing into its own separate universe. The implications are staggering. If the multiverse exists, it could explain why our universe seems so finely tuned for life. Perhaps in this vast cosmic landscape, we just happen to inhabit the one where the conditions are just right. But it also raises profound questions. Are there versions of us in these other universes? Do they experience time, space, and existence in ways we can't even imagine? The multiverse hypothesis doesn't just expand our understanding of the cosmos, it challenges us to rethink what it means to exist at all. Now, let's turn to one of the most profound mysteries in modern cosmology: dark matter and dark energy. These 2 enigmatic forces make up a staggering 95% of the universe, yet they remain invisible and largely unexplained. Dark matter, which makes up about 27% of the cosmos, doesn't emit, absorb, or reflect light, making it impossible to observe directly. So how do we know it's there? Its presence is inferred through its gravitational effects. Galaxies rotate faster than they should based on the visible matter alone, and galaxy clusters bend light in ways that suggest an unseen mass is at work. Then there's dark energy, which accounts for 68% of the universe. This mysterious force is driving the accelerated expansion of the cosmos. Unlike gravity, which pulls things together, dark energy seems to push everything apart. Scientists first detected its effects in the late 1990s when they observed that distant supernovae were fainter than expected, indicating the universe was expanding faster over time. Together, dark matter and dark energy shape the large-scale structure of the universe, from the distribution of galaxies to the cosmic web that connects them. Yet, despite decades of research, we still don't know what they are. Dark matter might consist of exotic particles that interact weakly with ordinary matter, while dark energy could be a property of space itself, like Einstein's cosmological constant. Or perhaps there's something entirely beyond our current understanding. What's clear is that unraveling these mysteries could revolutionize our knowledge of the universe, revealing patterns and principles we've yet to imagine. Now, let's journey back to the very beginning, the moment our universe burst into existence. The Big Bang Theory is the most widely accepted explanation for how the cosmos began. It suggests that around 13.8 billion years ago, the entire universe was concentrated into an infinitely dense point, a singularity. Then, in an instant, it expanded, setting the stage for everything we see today. But the story doesn't stop there. In the late 1970s, scientists proposed an addendum to the Big Bang Theory, cosmic inflation. This idea suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing unimaginably faster than the speed of light. This rapid inflation explains why the universe appears so uniform on large scales, and why we don't see extreme variations in temperature across the cosmos. Evidence for cosmic inflation comes from the cosmic microwave background, the afterglow of the Big Bang, which shows tiny fluctuations in temperature that align perfectly with predictions. However, cosmic inflation raises as many questions as it answers. What triggered this rapid expansion? Was it a one-time event, or could it happen again? Some theories even suggest that our universe might just be one of many, born from a multiverse of inflating bubbles. While the Big Bang and cosmic inflation provide a compelling framework for understanding the universe's origins, they leave us pondering the deeper mysteries of what came before and what lies beyond. Now, let's shift our gaze to a concept that bridges science and philosophy, the Anthropic Principle. This idea revolves around the observation that the fundamental constants and laws of the universe appear to be perfectly fine-tuned to allow life to exist. From the strength of gravity to the density of matter, even the slightest change in these values would make the cosmos inhospitable. For example, if the force of gravity were just a tiny bit stronger, stars would burn out too quickly, leaving no time for life to develop. If it were weaker, galaxies and stars might never have formed at all. This delicate balance has led some to wonder, is it mere coincidence, or is there something deeper at play? The Anthropic Principle offers two main perspectives. The first, known as the weak Anthropic Principle, suggests that we observe these constants because we exist in a universe that happens to support life. In other words, if the conditions weren't just right, we wouldn't be here to ask the question. The second, the strong Anthropic Principle, takes it a step further, proposing that the universe must have been designed or constrained in some way to permit life. This idea has sparked intense debate. Some argue it points to the existence of a creator, while others believe it supports the multiverse theory, that our universe is just one of countless others, each with its own set of laws, and we happen to live in the one that allows us to exist. Whether it's seen as evidence of design or a cosmic lottery, the Anthropic Principle challenges us to rethink our place in the universe and the nature of its hidden patterns. This raises profound questions about the origins of existence and whether life is a rare accident or an inevitable outcome of the cosmos design. Moving from the profound implications of the Anthropic Principle, let's explore another fascinating idea that might have shaped the universe in its earliest moments: cosmic strings. These are hypothetical, one-dimensional defects in spacetime, thought to have formed during the rapid expansion of the universe just after the Big Bang. Imagine the universe as a rapidly cooling material. Just as cracks or imperfections can form in ice as it freezes, cosmic strings are believed to be cracks in the fabric of spacetime itself. These structures are incredibly thin but could stretch across vast distances, even spanning the entire observable universe. Despite their immense scale, they'd be incredibly difficult to detect because they're so narrow and because their gravitational effects would be subtle. Scientists theorize that cosmic strings might have played a role in shaping the large-scale structure of the cosmos, influencing how galaxies and clusters of galaxies formed. Some even suggest that these strings could create detectable ripples in spacetime, known as gravitational waves, which we might someday observe with advanced instruments. However, cosmic strings remain purely theoretical for now. While they fit neatly into some models of the early universe, there's no direct evidence proving their existence. This makes them one of the most intriguing mysteries in cosmology, a tantalizing possibility that could help us understand the hidden patterns of our universe, but one that still lies just beyond our reach. Whether cosmic strings are real or not, they remind us how much we have yet to discover about the cosmos and its origins. Shifting our perspective from the physical fabric of the universe, let's dive into a theory that challenges the very nature of reality itself: the simulation hypothesis. This idea suggests that our universe might not be what it seems, but rather an incredibly advanced computer simulation created by a highly intelligent civilization. Think of it like this: if future humans or extraterrestrial beings developed technology capable of simulating entire worlds, complete with conscious beings, how would we know if we were one of those simulations? The concept isn't just science fiction. Philosophers like Nick Bostrom have proposed that if a civilization reaches a high enough level of technological advancement, it's statistically likely they would create simulations of their ancestors. And if that's the case, the odds are we're living in one of those simulations. From a scientific standpoint, some researchers have even suggested ways to test this theory. For example, if our universe is a simulation, there might be tiny pixels or glitches in the fabric of reality that we could detect with advanced technology. On the other hand, skeptics argue that simulating an entire universe with all its complexity would require an unimaginable amount of computational power, making the idea seem implausible. The simulation hypothesis also raises profound philosophical questions. If we are living in a simulation, does that make our experiences any less real? And if we someday create our own simulations, what does that say about the nature of existence? Whether or not this theory holds up, it invites us to think deeply about what it means to be real and how we understand the universe around us. As we continue to explore the cosmos, the simulation hypothesis reminds us that reality might be far more mysterious than we ever imagined. Moving on to one of the most intriguing questions in cosmology, let's explore the Fermi paradox. Given the sheer size of the universe, with hundreds of billions of galaxies each containing trillions of stars, it seems almost inevitable that intelligent life should exist somewhere beyond Earth. Yet, despite decades of searching, we've found no conclusive evidence of extraterrestrial civilizations. This contradiction is at the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everyone?" One possible explanation is that intelligent life is incredibly rare. The conditions needed for life to emerge, evolve, and develop advanced technology might be so specific that Earth is a cosmic anomaly. Another theory suggests that civilizations might self-destruct before they can develop the technology to communicate across vast distances, whether through war, environmental collapse, or other catastrophic events. On the other hand, it's possible that advanced civilizations exist, but we simply lack the technology to detect them. They might use communication methods we don't yet understand or have moved beyond the kinds of signals we're currently searching for. Some even propose that they might be deliberately avoiding contact with us, perhaps viewing humanity as too primitive or dangerous. The Fermi paradox doesn't just challenge our assumptions about life in the universe, it also forces us to confront our place in the cosmos. Are we alone, or are we just not looking hard enough? As we continue to scan the skies and develop new technologies, the search for answers to this paradox remains one of the most profound quests in science. Now, let's turn our attention to one of the most mind-bending phenomena in physics, quantum entanglement. Imagine two particles that are somehow connected, no matter how far apart they are in the universe. If you change one, the other instantly responds, even if they're light years apart. This strange connection is called quantum entanglement, and it challenges everything we thought we knew about space and time. At its core, entanglement suggests that the universe might be far more interconnected than we realize, with hidden threads binding particles across vast distances. Some scientists believe this phenomenon could reveal deeper patterns in the fabric of spacetime itself, hinting at a level of unity in the cosmos that we're only beginning to grasp. For example, entangled particles seem to defy the speed of light, raising questions about how information can travel instantaneously across space. This has led to theories that spacetime might not be the fundamental framework of the universe, but instead emerge from something even more basic, like a network of entangled connections. If true, entanglement could reshape our understanding of reality, suggesting that the universe operates more like a web of relationships than a collection of separate objects. The implications are profound, touching everything from black holes to the nature of existence itself. Could quantum entanglement be the key to unlocking the universe's hidden patterns? As we continue to explore this mysterious phenomenon, one thing is clear: the cosmos is far stranger and more interconnected than we ever imagined. Building on the strange and interconnected nature of quantum entanglement, let's now explore another cosmic mystery that pushes the boundaries of our understanding: the black hole information paradox. When we think of black holes, we often picture them as cosmic vacuums, gobbling up everything that crosses their event horizon, including light itself. But here's the puzzle: according to quantum mechanics, information about the state of matter cannot be destroyed. So, what happens to all the information about the particles that fall into a black hole? Does it vanish forever, or is there some way it escapes? This dilemma pits two of physics' greatest theories against each other: quantum mechanics, which insists that information is always preserved, and general relativity, which suggests that black holes erase it completely. To tackle this paradox, scientists have proposed some fascinating ideas. One prominent theory is the Holographic Principle, which suggests that all the information that falls into a black hole isn't lost but instead is encoded on its surface like a hologram. In this view, the event horizon acts as a two-dimensional boundary where the information is stored, preserving it even as the black hole devours everything inside. Another startling idea is the concept of firewalls, hypothetical walls of energy at the event horizon that would destroy anything falling into the black hole, effectively preserving information by not allowing it to enter in the first place. Both theories attempt to reconcile the conflict between quantum mechanics and general relativity, but neither has been fully proven. The black hole information paradox isn't just an academic exercise, it challenges our very understanding of the universe's rules. If information truly disappears in a black hole, it would mean our current laws of physics are incomplete. On the other hand, if it's preserved, we might be one step closer to uncovering the hidden patterns that govern reality. As we continue to probe the depths of black holes, this paradox reminds us that the universe is full of questions waiting to be answered, each one leading us closer to unraveling its deepest secrets. Shifting our focus to a radically different perspective, let's explore the ekpyrotic universe theory, a concept that challenges our traditional understanding of cosmic origins. Instead of a single explosive event like the Big Bang, this theory proposes that our universe was born from the collision of two higher-dimensional brains. Imagine brains as vast, thin sheets of energy and matter existing in a higher-dimensional space. According to this idea, when these brains collide, they release an enormous amount of energy, setting the stage for the formation of the universe as we know it. This theory offers a fascinating contrast to the Big Bang model. While the Big Bang suggests the universe began from an infinitely dense singularity, the ekpyrotic universe theory avoids this singularity altogether. Instead, it presents a smoother, more gradual process where the universe expands and evolves from the aftermath of the collision. Supporters of this theory argue that it provides a more elegant solution to some of the problems faced by the Big Bang theory, such as the singularity itself and the question of what came before the Big Bang. The implications of the ekpyrotic universe theory are profound. If true, it could reshape our understanding of cosmology by introducing the idea of higher dimensions and cyclical events. It also raises intriguing questions about the nature of reality. Could there be other universes formed from similar collisions? And if brains exist in higher dimensions, what else might be out there that we cannot see or comprehend? While this theory is still speculative and lacks definitive evidence, it offers a bold and imaginative alternative to the Big Bang, pushing us to think beyond the boundaries of our current understanding. As we continue to search for answers about the universe's origins, the ekpyrotic theory reminds us that the cosmos might be far more complex and interconnected than we ever imagined. It invites us to consider the possibility that our universe is just one piece of a much larger, multidimensional puzzle waiting to be unraveled, turning our attention to a concept that both baffles and fascinates scientists. We encounter the fine-tuning problem. This observation highlights that the fundamental constants of nature, such as the strength of gravity or the speed of light, appear to be perfectly calibrated to allow life to exist. Even the smallest deviation in these values would render the universe uninhabitable, raising the question, is this extraordinary precision mere coincidence, or does it point to something more profound? One perspective suggests that this fine-tuning might indicate a deeper, yet undiscovered, law of physics. Perhaps the constants are not arbitrary but governed by a hidden principle that naturally leads to a universe capable of supporting life. This idea aligns with the quest for a theory of everything, which seeks to unify the forces of nature into a single framework. If such a theory exists, it could explain why the constants are so precisely set, revealing a deeper order within the cosmos. On the other hand, the fine-tuning problem has led some to consider the multiverse hypothesis. According to this idea, our universe is just one of countless others, each with its own set of physical constants. In this vast ensemble, it's statistically inevitable that at least one universe would have the right conditions for life. While this theory offers an elegant explanation, it remains speculative as we currently lack direct evidence of other universes. The philosophical implications of the fine-tuning problem are equally intriguing. Does it suggest that the universe was designed with life in mind, or is it simply a result of random chance within a multiverse? These questions challenge us to rethink our understanding of existence and the role we play in the cosmos. As we explore the fine-tuning problem, we're reminded of the delicate balance that makes life possible. Whether it points to a deeper law of physics or a multiverse, this mystery invites us to ponder the profound interconnectedness of the universe and our place within it. And with that, we move to another fascinating theory that delves into the cosmic butterfly effect. Moving into the realm of cosmic unpredictability, let's explore how even the tiniest shifts in the early universe could have shaped the cosmos as we know it. This is the butterfly effect, a concept that originated in chaos theory, now applied to cosmology. Imagine the universe in its infancy, a hot, dense soup of energy and particles. In this primordial state, even the smallest fluctuation, a subtle variation in density or temperature, could ripple outward, creating profound consequences over billions of years. These minute changes laid the groundwork for the universe's large-scale structure. Slightly denser regions attracted more matter through gravity, eventually growing into the galaxies and galaxy clusters we observe today. Meanwhile, less dense areas became the vast cosmic voids that stretch across the cosmos. It's remarkable to think that the delicate balance of matter and energy we see now was shaped by variations so small they could have gone unnoticed in the universe's earliest moments. But what if those fluctuations had been just a little different? A slightly stronger gravitational pull in one region or a quicker expansion in another could have led to an entirely different universe. Galaxies might have formed in different patterns or perhaps not at all. The distribution of stars, planets, and even the building blocks of life could have been radically altered. This sensitivity to initial conditions highlights just how finely tuned the universe's evolution has been. The butterfly effect in cosmology also raises intriguing questions about the nature of the universe itself. Could these tiny fluctuations have been random, or were they guided by some deeper principle? Some scientists suggest they might be linked to quantum mechanics, where randomness plays a fundamental role. Others propose that they could be the echoes of processes we're yet to understand, hinting at a more intricate cosmic blueprint. As we consider the butterfly effect, we're reminded of the universe's delicate balance and the extraordinary chain of events that led to its current state. It's a testament to how even the smallest changes can have far-reaching consequences, shaping the cosmos on an unimaginable scale. And with that, we turn to another theory that invites us to rethink the nature of reality, the quantum multiverse. Building on the delicate balance of cosmic beginnings, let's venture into a theory that stretches the boundaries of imagination, the quantum multiverse. This idea suggests that every quantum event, every tiny decision made at the subatomic level, spawns an entirely new universe, creating an infinite web of parallel realities. Think of it this way: every time an electron moves, a photon is emitted or a particle decays. The universe doesn't just follow one path, it splits, with each possible outcome playing out in its own separate reality. At its core, this theory is rooted in quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales. In the quantum world, particles don't follow precise paths or definite states until they're observed. Instead, they exist in a haze of probabilities, a phenomenon known as superposition. The quantum multiverse takes this a step further, proposing that every possible outcome of these probabilistic events actually occurs, just in different universes. For instance, in one reality, you might choose to read this sentence, while in another, you've already moved on. The implications of this theory are staggering. If true, it would mean that every choice, every event, no matter how small, creates a branching tree of realities. There could be universes where history unfolded differently, where extinct species still thrive, or where entirely unknown forms of life exist. The quantum multiverse doesn't just suggest that these realities are possible, it insists they're inevitable, woven into the fabric of existence itself. But what does this mean for our understanding of reality? Philosophically, the quantum multiverse challenges our notions of free will and destiny. If every possible outcome happens, does our choice still matter? Some argue that it does, as each version of us makes decisions unique to their universe. Others see it as a reminder of the vast, interconnected nature of existence, where every action ripples across countless realities. This theory also raises questions about the nature of science. If we can't observe these parallel universes, how can we ever prove they exist? Some scientists point to the mathematics of quantum mechanics, which, while strange, has been remarkably accurate in predicting the behavior of particles. Others suggest that indirect evidence might one day emerge, perhaps through anomalies in the cosmic microwave background or unexplained quantum phenomena. As we contemplate the quantum multiverse, we're reminded once again of the universe's profound complexity. It's a theory that invites us to rethink not just the cosmos, but our place within it. And with that, we turn to another cosmic puzzle, the clues hidden in the afterglow of the Big Bang, known as the cosmic microwave background. Moving from the speculative realms of the quantum multiverse, we now turn our attention to a tangible piece of cosmic evidence, the cosmic microwave background. This faint glow, often referred to as the afterglow of the Big Bang, is one of the most significant discoveries in modern cosmology. It serves as a snapshot of the universe just 380,000 years after its birth, offering us a window into its earliest moments. The cosmic microwave background is essentially leftover radiation from the Big Bang, stretched and cooled over billions of years as the universe expanded. Today, it fills the entire cosmos in the form of microwaves, detectable by sensitive instruments like the Planck satellite. What makes this radiation so remarkable is its uniformity, but also its subtle variations. These tiny fluctuations, or anisotropies, are like cosmic fingerprints, encoding information about the universe's initial conditions and the processes that shaped its evolution. One of the key insights from studying the cosmic microwave background is its confirmation of the Big Bang theory. The uniformity of the background radiation supports the idea that the universe began as an incredibly hot, dense state which expanded and cooled over time. But the variations in temperature and density revealed by the data also provide clues about the seeds of cosmic structure. These irregularities would eventually grow into the galaxies, stars, and planets we see today, driven by the force of gravity. The cosmic microwave background also sheds light on the composition of the universe. By analyzing its properties, scientists have determined that ordinary matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the universe's total mass and energy. The rest is composed of dark matter and dark energy, mysterious entities that dominate the cosmos yet remain poorly understood. Another intriguing aspect of the cosmic microwave background is its ability to test theories about the universe's hidden patterns. For example, the precise measurements of its anisotropies have helped scientists refine models of cosmic inflation, the rapid expansion believed to have occurred in the universe's first fraction of a second. These observations have also provided evidence for the overall geometry of the universe, suggesting it is flat on large scales, a finding with profound implications for cosmology. As we explore the cosmic microwave background, we're reminded of how much the universe's origins are etched into its very fabric. This ancient radiation not only tells the story of the Big Bang, but also hints at the processes that continue to shape the cosmos today. And with that, we prepare to delve into another gravitational mystery, the Great Attractor, a cosmic anomaly that's pulling galaxies toward it with irresistible force. Shifting our focus from the cosmic microwave background, we now encounter one of the universe's most puzzling gravitational phenomena, the Great Attractor. Located in the direction of the Centaurus and Hydra constellations, this colossal gravitational anomaly exerts a powerful pull on galaxies, including our own Milky Way. It's as if there's a hidden force in space tugging everything toward it, yet its true nature remains shrouded in mystery. The Great Attractor's existence was first inferred in the 1970s and 80s when astronomers noticed that galaxies in our local neighborhood were moving in a peculiar way. Instead of expanding uniformly with the universe, they were all drifting toward a specific region of space. This unusual motion suggested the presence of an immense concentration of mass, one that couldn't be explained by the visible matter we observe. One of the biggest challenges in studying the Great Attractor lies in its location. It sits behind the plane of our Milky Way galaxy, an area dense with stars, gas, and dust that obscures our view. This region, known as the zone of avoidance, makes it incredibly difficult to observe the Great Attractor directly using traditional optical telescopes. To overcome this, scientists rely on other wavelengths of light, such as infrared and radio, which can penetrate the galactic haze and provide a clearer picture. Current observations suggest that the Great Attractor is not a single object, but rather a massive cluster of galaxies, along with vast amounts of dark matter. This dense concentration of mass creates a gravitational pull strong enough to influence the motion of galaxies across hundreds of millions of light years. However, even this explanation doesn't fully account for the Great Attractor's immense influence, leading scientists to speculate that it might be part of an even larger structure, such as the Laniakea supercluster, a colossal network of galaxies that spans over 500 million light-years. The Great Attractor also raises questions about the universe's large-scale structure and the role of dark matter. Its existence hints at how matter, both visible and dark, is distributed across the cosmos, shaping the movements of galaxies on an enormous scale. By studying this gravitational anomaly, scientists hope to uncover more about the forces that govern the universe and how its hidden patterns are woven into the fabric of space. As we delve deeper into the mysteries of the Great Attractor, we're reminded of how much of the universe remains unseen and unexplained. This gravitational enigma not only challenges our understanding of cosmic structures, but also invites us to explore the hidden forces that shape the cosmos. And with that, we turn our attention to another fundamental question: why the universe is made mostly of matter with barely any antimatter, a puzzle known as the Baryon asymmetry problem. Turning our attention to another profound mystery of the cosmos, we encounter the Baryon asymmetry problem. This puzzle revolves around a simple yet baffling observation. Our universe is overwhelmingly made of matter, with almost no antimatter to be found. But why, according to the laws of physics, matter and antimatter should have been created in equal amounts during the Big Bang? Yet, as we look around, there's no trace of the vast amounts of antimatter that should exist. This imbalance is one of the most significant unsolved questions in modern physics. To understand this problem, let's start with the basics. Matter and antimatter are like mirror images of each other. When they meet, they annihilate, releasing energy. In the early moments of the universe, conditions were so extreme that particle collisions created both matter and antimatter in abundance. So, if they were produced in equal amounts, why didn't they completely annihilate each other, leaving behind nothing but energy? Somehow, a slight excess of matter survived, and it's this tiny surplus that makes up everything we see today: stars, planets, and even ourselves. Scientists have been working tirelessly to explain this asymmetry. One leading theory is called baryogenesis. It suggests that certain processes in the early universe favored the creation of matter over antimatter. These processes might have involved violations of fundamental symmetries in physics, such as charge parity symmetry, which governs how particles behave under certain transformations. Essentially, the universe might have broken the rules in its infancy, tipping the scales in favor of matter. Another intriguing possibility involves neutrinos, those elusive particles that barely interact with matter. Some theories propose that neutrinos and their antimatter counterparts, antineutrinos, might not be perfectly symmetric. If neutrinos behave slightly differently from antineutrinos, this could have contributed to the matter-antimatter imbalance. Experiments like those conducted at the Large Hadron Collider are actively testing these ideas, searching for clues in the behavior of particles and antiparticles. The Baryon asymmetry problem isn't just a curiosity, it's a cornerstone of our understanding of the universe. Without this imbalance, matter and antimatter would have annihilated each other completely, leaving behind a universe devoid of galaxies, stars, or life. Solving this mystery could reveal fundamental truths about the nature of reality and the forces that shape the cosmos. As we ponder this profound question, we're reminded of how much remains to be discovered about the universe's origins. From the smallest particles to the largest structures, every piece of the puzzle brings us closer to understanding the hidden patterns that govern existence. And with that, we turn to another fascinating theory, the Omega Point theory, which explores the universe's ultimate destiny. Now, shifting our gaze toward the far future of the cosmos, we encounter the Omega Point theory. This fascinating concept proposes that the universe is on a trajectory toward a final state of infinite complexity and consciousness. It's a theory that bridges the gap between physics and philosophy, offering a profound vision of where everything might be headed. The Omega Point theory was initially developed by physicist Frank Tipler, who combined ideas from cosmology, computer science, and theology to paint a picture of the universe's ultimate destiny. At its core, the theory suggests that as the universe continues to expand and evolve, it will eventually reach a state of maximum complexity and information processing. This final state, known as the Omega Point, would represent a culmination of all possible knowledge and experiences, effectively becoming a form of cosmic consciousness. From a physics perspective, the theory ties into the concept of the Big Crunch, a hypothetical scenario where the universe stops expanding and begins to collapse back in on itself. Tipler argued that as the universe approaches this final collapse, the energy density would increase exponentially, allowing for an infinite amount of computational power. This, in turn, would enable the universe to simulate or embody all possible thoughts and experiences, essentially becoming a kind of universal mind. Philosophically, the Omega Point theory touches on deep questions about purpose and existence. It suggests that the universe's evolution isn't random but is instead guided toward an ultimate goal, the realization of infinite consciousness. Some interpretations even draw parallels with religious ideas of transcendence or union with a divine presence, though the theory itself remains rooted in scientific principles. Critics of the Omega Point theory point out that it relies on speculative assumptions, such as the inevitability of a big crunch, which is not supported by current observations of the universe's accelerating expansion. However, the theory continues to inspire thinkers across disciplines, offering a unique lens through which to imagine the cosmic future. What makes the Omega Point theory so compelling is its audacity. It dares to suggest that the universe's story doesn't end in chaos or emptiness, but in a state of infinite potential. Whether or not this vision proves true, it challenges us to think beyond the limits of our current understanding and imagine what the cosmos might still become. With this thought in mind, let's now turn to another intriguing aspect of the universe's structure, the large-scale cosmic web and its role in shaping the distribution of galaxies and matter across the vast expanse of space. Turning our attention to the grand architecture of the universe, we encounter the cosmic web, a sprawling network of galaxies, dark matter, and vast voids that defines the large-scale structure of our cosmos. This intricate tapestry, stretching across billions of light-years, offers a glimpse into the universe's fundamental organization and the forces that shaped it from its earliest moments. The cosmic web's origins trace back to the Big Bang, when the universe was a hot, dense soup of particles and energy. As the universe expanded and cooled, tiny fluctuations in density began to emerge, seeded by quantum processes in those first fractions of a second. Over billions of years, gravity amplified these fluctuations, pulling matter into dense regions that eventually collapsed to form galaxies, while leaving behind vast, empty voids. Dark matter, the mysterious substance that makes up about 27% of the universe, plays a crucial role in this process. Its gravitational pull acts as the cosmic scaffolding, guiding the formation of the web's filaments and nodes. Galaxies and clusters of galaxies form at the intersections of these filaments, like glittering beads strung along invisible threads, while the voids between them remain eerily empty. The cosmic web isn't just a static structure, it's a dynamic, evolving system. Galaxies and clusters move along the filaments drawn by gravity, and collisions between clusters release immense amounts of energy, reshaping the web over time. This ongoing dance of matter and energy reveals the universe's history and provides clues about its ultimate fate. By studying the cosmic web, scientists can learn more about the nature of dark matter and dark energy, as well as the processes that govern the universe's evolution. Observations of galaxy distributions and the bending of light from distant objects, known as gravitational lensing, help map the web's structure and test our understanding of cosmology. What makes the cosmic web so fascinating is its scale and complexity. It's a reminder that the universe is more than just a random scattering of stars and galaxies. It's a highly organized system, shaped by the interplay of fundamental forces. As we continue to explore this vast network, we uncover deeper insights into the cosmos and our place within it. With this understanding of the universe's large-scale structure in mind, let's now turn to another intriguing concept: the Planck scale, where the smallest units of space and time challenge our understanding of reality itself. Now, let's zoom into the very fabric of reality itself, where the rules of physics as we know them break down the Planck scale. This is the realm of the unimaginably small, where distances are measured in units so tiny they're almost beyond comprehension. At this scale, quantum mechanics and gravity, the two pillars of modern physics, must somehow come together, even though they seem fundamentally incompatible in our everyday world. The Planck length, roughly 1/1,000,000,000 of a trillionth of the size of an atom, marks the point where our understanding of space and time collapses. Here, the smooth, continuous fabric of spacetime predicted by Einstein's theory of general relativity gives way to a turbulent, fluctuating sea of quantum foam. It's a place where particles flicker in and out of existence, and gravity, which we experience as a gentle force, becomes as intense as the other fundamental forces. To make sense of this chaotic realm, physicists have proposed groundbreaking theories like string theory and loop quantum gravity. String theory suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings, oscillating at different frequencies, give rise to all the particles and forces we observe. It's a beautiful idea, but one that requires extra dimensions of space, far beyond the three we're familiar with, to work mathematically. On the other hand, loop quantum gravity takes a different approach. Instead of strings, it envisions spacetime as a network of interconnected loops forming a kind of cosmic mesh. In this framework, space isn't smooth but granular, made up of discrete, indivisible units. This idea could resolve the conflict between quantum mechanics and gravity by providing a quantum description of spacetime itself. Both theories aim to unify the forces of nature and provide a complete picture of reality, but so far, neither has been proven. The Planck scale is so far removed from our everyday experience that testing these ideas experimentally is incredibly challenging. Still, they represent our best attempts to answer some of the deepest questions in physics. What is spacetime made of? How does gravity work at the smallest scales? And what lies beyond the limits of our current understanding? As we continue our exploration of the universe's hidden patterns, these theories remind us that even the most fundamental aspects of reality remain shrouded in mystery. Next, we'll examine another perplexing question: why time seems to flow in only one direction, and what that might tell us about the nature of the cosmos. Stepping into the realm of time, we encounter one of the most puzzling questions in physics. Why does time move forward? At first glance, it might seem obvious: we're born, we grow, and we age. But when we look at the laws of physics, they don't actually favor one direction of time over the other. Newton's equations, Einstein's relativity, and even quantum mechanics work just as well whether time flows forward or backward. So why does time feel like a one-way street? The answer might lie in a concept called entropy, often described as the measure of disorder in a system. The second law of thermodynamics tells us that in a closed system, entropy always increases over time. Imagine a cup of coffee sitting on a table. It starts hot and orderly, but as time passes, it cools down and its heat spreads into the surrounding air, increasing entropy. This tendency toward disorder is what gives time its arrow. But why does entropy increase? Some scientists point to the Big Bang as the starting point. In the early universe, everything was packed into an incredibly dense, high-energy state, a state of low entropy. As the universe expanded and cooled, entropy began to rise. This initial condition set the stage for time's one-way flow, creating a cosmic trend toward disorder that continues to this day. However, this still leaves us with questions. Why was the early universe in such a low entropy state? Some theories suggest it might have been a random fluctuation, while others propose that our universe is just one part of a larger multiverse, where other universes might have different arrows of time. Interestingly, the arrow of time isn't just a cosmic quirk, it's deeply tied to our experience of reality. Our memories, aging, and even the way we perceive cause and effect are all shaped by time's forward march. Without it, the universe as we know it wouldn't make sense. So, while the laws of physics might be time-symmetric, the arrow of time reminds us that the universe has a story to tell, one that began with the Big Bang and continues to unfold with every passing moment. Next, we'll dive into another mystery, the vacuum catastrophe, and why the energy of empty space doesn't add up. Now, let's turn our attention to one of the most baffling discrepancies in modern physics, the vacuum catastrophe. At first glance, empty space might seem like just that, empty. But according to quantum field theory, the vacuum of space isn't truly empty at all. Instead, it's a seething, dynamic arena filled with virtual particles that constantly pop in and out of existence. These quantum fluctuations are thought to contribute to the energy of empty space, often referred to as vacuum energy or the cosmological constant. Here's where things get puzzling. When physicists calculate the predicted energy of empty space based on quantum field theory, the result is astonishingly large, an unimaginably high number that dwarfs anything we've ever observed. But when we measure the actual energy of empty space through observations of the universe's expansion, the value is shockingly small, nearly zero. This glaring mismatch between prediction and observation is what's known as the vacuum catastrophe, and it's one of the biggest unsolved problems in physics. So, why does this matter? Well, vacuum energy plays a critical role in our understanding of the universe's expansion. Einstein first introduced the cosmological constant to explain a static universe, but later discoveries showed that the universe is actually expanding at an accelerating rate. This acceleration is often attributed to dark energy, which could be linked to vacuum energy. But if our calculations of vacuum energy are so wildly off, it raises serious questions about our understanding of quantum mechanics and gravity. One possible explanation is that there's a cancellation mechanism at work, some unknown principle that precisely cancels out the enormous predicted energy, leaving behind the tiny value we observe. Others suggest that our theories might be incomplete, requiring a new framework that bridges the gap between quantum mechanics and general relativity. Some even propose that this discrepancy hints at the existence of extra dimensions or undiscovered fields that modify the behavior of empty space. The vacuum catastrophe isn't just a technical problem, it's a profound challenge to our understanding of the cosmos. It forces us to confront the limits of our current theories and pushes us to explore new ideas that could revolutionize physics. As we continue to probe the mysteries of empty space, one thing is certain: the vacuum isn't as empty as it seems, and the secrets it holds could reshape our understanding of reality itself. Next, we'll explore another elusive mystery, the nature of dark matter and the search for weakly interacting massive particles. Now, shifting our focus to another cosmic mystery, let's dive into the intriguing concept of weakly interacting massive particles, or WIMP. These hypothetical particles are one of the leading candidates for explaining the nature of dark matter, which makes up about 27% of the universe. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its gravitational effects are unmistakable, influencing the rotation of galaxies and the bending of light in the cosmos. So, what exactly are WIMP, and why do scientists believe they might hold the key to unlocking the secrets of dark matter? WIMP are thought to be incredibly heavy particles, much more massive than protons or neutrons. Despite their size, they interact with ordinary matter extremely weakly, almost exclusively through gravity. This makes them nearly impossible to detect directly, which is why experiments designed to find them require incredibly sensitive equipment. Scientists have set up detectors deep underground, shielded from cosmic rays and other interference, in the hope of catching a rare interaction between a WIMP and an atom. So far, no definitive detection has been made, but the search continues with ever more advanced technology. One of the reasons WIMP are such a compelling candidate for dark matter lies in their theoretical origins. They naturally emerge from certain extensions of the standard model of particle physics, such as supersymmetry, which predicts the existence of heavier partner particles for every known particle. If these particles exist, they could have been produced in abundance during the early universe and persisted to this day, forming the invisible scaffolding that holds galaxies together. This elegant connection between particle physics and cosmology is what drives much of the enthusiasm for the WIMP hypothesis. But the mystery deepens when we consider alternative explanations. What if WIMP don't exist and dark matter is made of something entirely different? Some researchers are exploring other possibilities, such as actions or sterile neutrinos, particles that could also explain dark matter's effects. However, WIMP remain a favorite due to their theoretical appeal and the ongoing efforts to detect them. The hunt for these elusive particles isn't just about solving a cosmic puzzle, it's about expanding our understanding of the fundamental building blocks of the universe. As experiments grow more sophisticated and our theories evolve, we inch closer to uncovering the true nature of dark matter. Whether WIMP are the answer or we need to rethink our approach entirely, the journey to solve this mystery is a testament to humanity's relentless curiosity and drive to understand the cosmos. Next, we'll explore another mind-bending theory, the possibility that our universe could exist inside a black hole. Now, let's venture into a theory that stretches the boundaries of our imagination, the possibility that our universe might exist inside a black hole. This idea, known as the black hole universe theory, suggests that the cosmos we inhabit could be the interior of a black hole in a larger parent universe. It's a concept that turns our understanding of reality on its head, but it's rooted in some fascinating scientific principles. The theory draws inspiration from the way black holes work. When matter falls into a black hole, it's crushed into an infinitely dense point called a singularity. But what happens beyond that point? Some physicists propose that instead of being a dead end, a singularity could give rise to an entirely new universe. In this scenario, the immense gravitational forces inside a black hole could trigger a kind of cosmic rebirth, expanding into a new space and time separate from the original universe. One piece of evidence that supports this idea comes from the study of black hole thermodynamics. In the same way that black holes have entropy, a measure of disorder, our universe also appears to have a certain amount of entropy. This similarity hints at a possible connection between the two. Additionally, the Big Bang, which marks the beginning of our universe, shares some striking similarities with the formation of a singularity. Both involve an incomprehensibly dense state of matter and energy, leading some to wonder if the Big Bang was the result of a black hole in another universe. The implications of this theory are profound. If our universe is inside a black hole, it raises questions about the nature of reality itself. Are there other universes nested within black holes in our own cosmos? Could our universe also harbor black holes that contain entirely separate realities? This idea suggests a potentially infinite hierarchy of universes, each contained within the black holes of another. Of course, this theory is still highly speculative, and there's much we don't understand about black holes and the nature of singularities. However, it's a compelling perspective that challenges us to think beyond the confines of our observable universe. Whether or not the black hole universe theory holds true, it reminds us that the cosmos is filled with mysteries waiting to be unraveled. Next, we'll explore another fascinating idea, the Gaia hypothesis and its cosmic implications. Moving from the mind-bending black hole universe theory, let's shift our focus to a concept that brings us closer to home, the Gaia hypothesis. This intriguing idea proposes that Earth functions as a self-regulating system, almost like a living organism. Developed by scientist James Lovelock in the 1970s, the hypothesis suggests that Earth's biosphere, the sum of all living organisms, interacts with the physical environment to maintain conditions suitable for life. It's a perspective that sees our planet not as a passive stage for life, but as an active participant in sustaining it. The Gaia hypothesis points to examples like the regulation of Earth's temperature, the balance of oxygen and carbon dioxide in the atmosphere, and the cycling of nutrients through ecosystems. These processes, Lovelock argues, are not random but part of a complex, self-regulating system. For instance, even when external factors like solar radiation change, Earth systems adjust to keep conditions within a range that supports life. This idea challenges the traditional view of nature as a collection of separate parts, instead presenting it as an interconnected whole. But what if this concept extends beyond Earth? Could the universe itself operate like a living system? Some thinkers have drawn parallels between the Gaia hypothesis and the idea of a living universe. In this view, the cosmos might possess its own form of self-regulation, with galaxies, stars, and planets interacting in ways that maintain cosmic balance. For example, the life cycles of stars, which generate the elements necessary for life, could be seen as part of a larger, self-sustaining process. This perspective raises profound questions about the nature of existence. If the universe is a living system, does it have a purpose or consciousness? Or is it simply a complex network of interactions that sustain its own continuity? While these ideas remain speculative, they invite us to rethink our place in the cosmos, not as isolated observers but as part of a larger, dynamic whole. The Gaia hypothesis, whether applied to Earth or extrapolated to the universe, reminds us of the intricate connections that sustain life and existence. It's a theory that bridges science and philosophy, offering a fresh lens through which to view the cosmos. As we continue our exploration of hidden patterns in the universe, we'll next delve into the mysterious false vacuum theory and its potentially dramatic implications. Now, let's venture into a theory that could change everything we know about the universe, the false vacuum theory. This idea suggests that our universe might not be in its most stable state. Instead, it could be in what scientists call a metastable condition, like a bubble that appears solid but could pop at any moment. If this bubble were to burst, the consequences would be nothing short of catastrophic. To understand this, imagine the universe's vacuum, the empty space between stars and galaxies, as a kind of energy field. This field might not be in its lowest possible energy state, which physicists refer to as the true vacuum. Instead, it could be in a false vacuum, a higher energy state that's stable for now but potentially unstable in the long run. If a quantum event were to trigger a shift from the false vacuum to the true vacuum, it could unleash a wave of destruction across the cosmos. This process, known as vacuum decay, would start at a single point and expand outward at the speed of light. As it spreads, it would rewrite the fundamental laws of physics, altering everything from the forces that hold atoms together to the behavior of light itself. Stars, planets, and even life as we know it could be annihilated in an instant. The universe as we understand it would cease to exist, replaced by a new reality governed by entirely different rules. The false vacuum theory isn't just a thought experiment, it's grounded in the principles of quantum field theory. While the chances of such an event happening are incredibly low, the sheer scale of the universe means it's not entirely impossible. This theory challenges us to think about the fragility of existence and the potential for sudden, irreversible change on a cosmic scale. So, what does this mean for us? On one hand, it's a humbling reminder of how little we truly understand about the universe. On the other, it's an invitation to explore the deeper mysteries of reality, pushing the boundaries of science and philosophy. As we continue to unravel the hidden patterns of the cosmos, we'll next examine the intriguing axis of evil and how it might challenge our understanding of the universe's origins. Now, let's shift our focus to one of the most puzzling anomalies in cosmology, the axis of evil. This term might sound dramatic, but it refers to a mysterious pattern found in the cosmic microwave background, the faint afterglow of the Big Bang. Scientists noticed that certain features in this radiation appear to align in a way that defies expectations, raising questions about our fundamental understanding of the universe. The cosmic microwave background is like a snapshot of the universe when it was just 380,000 years old. It's filled with tiny temperature fluctuations that provide clues about the early cosmos and its evolution. According to the standard model of cosmology, these fluctuations should be randomly distributed with no preferred direction or alignment. However, the axis of evil suggests that some of these features are not random at all, but instead seem to align along a specific axis. This alignment challenges the cosmological principle, which states that the universe should look the same in all directions on a large scale. If the axis of evil is real, it could mean that the universe has a preferred orientation or that our understanding of its origins is incomplete. Some scientists propose that this pattern could be a clue to new physics, such as the influence of gravitational waves from a pre-Big Bang era or even evidence of a multiverse. However, not everyone is convinced. Some argue that the axis of evil could be a statistical fluke or an artifact of the way we measure the cosmic microwave background. Others suggest that it might be related to the motion of our solar system through the universe, which could skew our observations. Despite the debate, the axis of evil remains a fascinating mystery that continues to intrigue cosmologists. This discovery reminds us that even our most established theories can be called into question by new evidence. It's a testament to the ever-evolving nature of science and the importance of keeping an open mind. As we continue our journey through the universe's hidden patterns, we'll next explore the idea that the cosmos might be fundamentally built on information, with physical laws emerging from computational processes. Building on the mysteries of the cosmos, we now turn our attention to a theory that flips our understanding of reality on its head, the concept of the information-theoretic universe. Imagine for a moment that everything around us, the stars, the planets, even you and I, are not just physical entities but manifestations of information. This idea suggests that the universe might be fundamentally built on bits of data, with the laws of physics emerging from computational processes rather than material substance. At the heart of this theory is the notion that information is the most basic building block of reality. Just as a computer processes data to create simulations, the universe might operate like a vast, intricate computational system. Every particle, every force, and every interaction could be seen as the result of information being processed and transformed. This perspective shifts the focus from matter and energy to the abstract concept of information, challenging our traditional views of how the cosmos works. One of the key proponents of this idea was physicist John Wheeler, who famously coined the phrase "it from bit." He proposed that every component of the physical world, from the tiniest quark to the largest galaxy, ultimately derives its existence from the answers to yes or no questions, binary bits of information. This radical idea has inspired further exploration into how information might shape the fabric of reality. Supporters of the information theoretic universe argue that this framework could help unify physics, bridging the gap between quantum mechanics and general relativity. It offers a new way to understand phenomena like black holes, where information seems to vanish, and quantum entanglement, where particles remain connected across vast distances. If the universe is indeed a computational system, these mysteries might be clues to its underlying code. However, this theory is not without its skeptics. Critics question whether information alone can explain the richness and complexity of the physical world. They also point out that the idea remains largely theoretical, with no direct experimental evidence to confirm it. Still, the information theoretic universe continues to inspire scientists and philosophers alike, pushing us to rethink the very nature of existence. As we ponder this idea, it's worth considering how it might change our view of the cosmos. Could the universe be a grand computation, with every event and object the result of data processing? And if so, what does that mean for our place within it? These questions lead us to the next intriguing theory in our exploration of the universe's hidden patterns: the concept of a cyclic universe, where the cosmos undergoes endless cycles of expansion and contraction. Now, let's turn our attention to a theory that takes our understanding of the universe's origins in a whole new direction: the idea of a cyclic universe. Unlike the Big Bang theory, which suggests a singular beginning, the cyclic universe proposes that the cosmos undergoes endless cycles of expansion and contraction, like a cosmic heartbeat that never stops. This model offers a fascinating alternative to the idea of a one-time Big Bang, suggesting instead that the universe might be eternal, rebounding and renewing itself over and over. At the core of this theory is the concept that the universe doesn't have a definitive starting point, but rather follows a repeating pattern. Each cycle begins with a period of rapid expansion, similar to the Big Bang, but instead of ending in heat death or a big crunch, the universe contracts back to a highly dense state, only to expand again in a new cycle. This process could potentially continue indefinitely, creating a universe without a true beginning or end. One of the most compelling aspects of the cyclic universe theory is its ability to address some of the limitations of the Big Bang model. For example, the Big Bang theory struggles to explain what caused the initial explosion or what might have existed before it. The cyclic universe sidesteps this issue by suggesting that there's no singular beginning, just an endless series of cosmic rebirth. Additionally, this model could explain why the universe appears so finely tuned for life, as each cycle might naturally select for conditions conducive to complexity and structure. Evidence supporting the cyclic universe is still speculative but intriguing. Some scientists point to the distribution of matter in the universe, which appears to follow patterns that could align with a cyclical process. Others look to the cosmic microwave background, the afterglow of the Big Bang, for clues. Tiny anomalies in this radiation might hint at a previous cycle, suggesting that our universe isn't the first but part of an infinite sequence. However, the cyclic universe theory is not without its challenges. Critics argue that it's difficult to test or prove, as the evidence remains indirect. There's also the question of how the universe transitions from contraction to expansion without violating known physical laws. Despite these hurdles, the theory continues to captivate scientists and philosophers, offering a bold reimagining of the cosmos. As we consider the implications of a cyclic universe, it raises profound questions about the nature of time, existence, and the ultimate fate of everything we know. Could the universe be an eternal dance of creation and destruction? And if so, what does that mean for our place within this grand cycle? These questions lead us to the final theory in our exploration: a thought-provoking idea that connects the nature of reality to the very fabric of consciousness itself. Now, let's venture into the final and perhaps most mind-bending theory in our exploration, one that ties the very fabric of reality to the power of consciousness itself. This idea suggests that consciousness isn't just a byproduct of the universe, but a fundamental force that shapes it. Imagine for a moment that the cosmos isn't just a cold, indifferent expanse, but a living, responsive entity molded by the minds that observe it. This concept, often referred to as the consciousness-created universe, bridges the gap between philosophy and quantum mechanics, offering a radical rethinking of existence. At the heart of this theory is the observer effect in quantum mechanics, which reveals that the act of observation can influence the behavior of particles. For example, in the famous double-slit experiment, particles behave differently when they are being watched, almost as if they know they are being observed. This has led some scientists and philosophers to speculate that consciousness itself might be a key ingredient in the universe's structure. Could it be that reality only takes a definitive form when it's observed? And if so, what does that mean for the nature of existence? The implications of this idea are profound. It suggests that the universe isn't a static, predetermined entity, but a dynamic, participatory one. Every act of observation, every conscious thought, could be subtly shaping the reality we experience. This theory also raises questions about the nature of reality itself. Is the universe a purely physical construct, or is it something more, a collaborative creation between the physical world and the minds that perceive it? Proponents of the consciousness-created universe point to the mysterious nature of quantum mechanics as evidence. The strange, counterintuitive behavior of particles at the quantum level seems to defy classical physics, hinting at a deeper, more interconnected reality. Some even suggest that consciousness might be a fundamental property of the universe, like space or time, existing alongside the physical laws we're familiar with. Of course, this theory is not without its skeptics. Critics argue that it's difficult to test or prove, as consciousness itself remains one of the great mysteries of science. There's also the question of how such a theory could be reconciled with the objective, measurable aspects of the universe. Despite these challenges, the idea continues to captivate thinkers across disciplines, offering a bold and imaginative perspective on the nature of reality. As we conclude our journey through these 30 theories, one thing becomes clear: the universe is far more mysterious and interconnected than we might have imagined. From the holographic principle to the consciousness-created universe, each theory challenges our understanding of existence and invites us to see the cosmos in a new light. The patterns we've explored, whether hidden in the fabric of spacetime or woven into the nature of consciousness, reveal a universe that is endlessly fascinating, endlessly complex, and endlessly inspiring. So, what do you think about these theories? Do they resonate with your understanding of the cosmos, or do they leave you with even more questions? Let us know in the comments, and don't forget to subscribe for more deep dives into the mysteries of the universe. As we wrap up this journey through the mysteries of the cosmos, it's worth reflecting on just how interconnected and diverse these 30 theories truly are. From the mind-bending concept of the holographic universe to the tantalizing idea of a consciousness-created reality, each theory offers a unique lens through which to view the hidden patterns of existence. Together, they paint a picture of a universe that is far more complex, dynamic, and mysterious than we often realize. These ideas don't just stand alone, they weave together, forming a tapestry of thought that challenges our understanding of space, time, and reality itself. What's truly remarkable is how these theories push the boundaries of science and philosophy, inviting us to question what we think we know. They remind us that the universe is not a static, predictable place, but a living, evolving mystery, full of secrets waiting to be uncovered. Whether it's the enigma of dark matter, the paradoxes of quantum mechanics, or the cosmic implications of consciousness, each theory sparks curiosity and wonder, driving us to explore further and think deeper. But the journey doesn't end here. These theories are not just answers, they're invitations to keep asking questions. What do you think about these ideas? Do they challenge your understanding of the universe or spark new theories of your own? Share your thoughts in the comments below. We'd love to hear your perspective. And if you've enjoyed this deep dive into the cosmos, don't forget to subscribe and hit the notification bell for more explorations into the mysteries of the universe. Together, let's keep unraveling the hidden patterns of existence, one theory at a time.